let's do some examples of naming some ionic binary compounds. This is binary, meaning two species. To name a compound, you must know if it is a molecular or ionic compound so that you know which rules to follow. If you have a metal, nonmetal, or polyatomic ion, it is an ionic compound where you name the metal first, then the nonmetal, or changing the ending to IDE. If it is a transition metal, you must include the charge of the metal in Roman numerals. If you have a nonmetal, it is a molecular compound, which we haven't discussed yet. But it's important for you to realize what type of bonding is going on for you to decide which way to name the compound. Looks like sodium NaF. Okay? That's a metal and a nonmetal, so this is ionic bonding, so we're going to follow ionic rules. In that, we say we name the metal by its name, and then we name the anion with IDE changed on the end. So in this case, it's going to be sodium fluoride. Now notice the spelling in fluoride, it's Fluoride. That's very important as you go on online homework. There's boxes for you to put in the names. You have to spell them correctly. There's also boxes for the parentheses of the Roman numerals. There would be a box to put one parentheses, then the Roman numerals in each one, and then closed parentheses. So make sure that you've put in the stuff correctly into the boxes. Let's look at lithium chloride. Now I got the name, I want to get to the formula. So to do this, you have to know what's the charges. We know lithium is in a group 1, so lithium is a +1, and chlorine is a -1. So if we want to balance those charges, we need one of each species. Therefore, the formula would be simply LiCl. Magnesium and oxygen. Well, to write the formula, we need to write the name of the first species, which is magnesium, and then the second one is oxygen, which we changed it to IDE ending, which means this would be magnesium oxide. Next one, we got MnBr2. Mn is a transition metal, manganese. So if I'm going to write the formula, I need to write the oxidation number of that manganese. So I need to calculate that. We know bromide is always -1. There's 2 of them, so that's a total of a 2-. That means this manganese must have a 2+ charge on it, and I'm going to have to put that in Roman numerals. So this would be manganese, Roman numeral 2, bromide. As I said on the homework, you would type in manganese, each letter, then there would be a block for that parentheses. There'd be a block for the Roman numeral 1, another block for the Roman numeral 1 again, and then another block for the closed parentheses, as well as the rest of the word for bromide. Cobalt 3 oxide. This is written in words, so this cobalt 3 is telling me the charge of cobalt. Okay, so that's telling me that I have a cobalt 3+ charge. And we know that oxide is oxygen with a 2-. So now I got to put those together to get my formula, which would mean I have cobalt subscript 2, oxygen subscript 3 to get a total of a +6 and -6 to get them to cancel. Ends up cobalt subscript 2, oxygen subscript 3. Now I have copper 2 chloride, or cupric chloride using the older name. The copper is telling me I have a 2+ charge on copper. We know chloride is -1. Well, the formula in this case can end up being CuCl subscript 2. A polyatomic ion is an ion consisting of 2 or more atoms chemically bonded together and carrying a net electrical charge. We name the compound the same way we just described, except each polyatomic ion has its own particular name. Books typically have tables that list common polyatomic ions. Most are oxyanions, meaning species that consist of oxygen with another element as the central element. Example, NO3 minus, NO2 minus, nitrate ion and nitrite ion. SO4 2 minus, sulfate, SO3 2 minus, sulfite. Notice something here, that they have similar charge, nitrate and nitrite. Okay, -1, sulfate, sulfite has the same charge, -2 minus. The difference is the number of oxygens. And as we change the number of oxygens, we change the ending. You can see for the nitrate has the higher oxidation number of oxygens, sulfate the higher number, also has the ATE. Most groups have ate and ite endings and differ by the number of oxygens. And that's just to help you out in the memorization process of learning these polyatomic ions. Another thing to know about is that some groups, manganese, bromine, chlorine, and iodine, have per 8 as the largest one a number of oxygens. Then you have an 8, lost one oxygen, lost another oxygen, you have the ite, lost another oxygen, you have the hypoite ions. Example of what I just talked about would be your chlorine here. You see I have ClO4 minus. If I memorize that as perchlorate ion, I know if I lose an oxygen, it's chlorate, same oxidation state, -1. Lose another oxygen, same oxidation state, -1. I have the chlorite. Lose another one, I'm at hypochlorite. You should learn these polyatomic ions. Most of them are anions, only a couple of them are cations. You have ammonia ion and a mercury 1 or mercurous ion. Most of them do not have endings of IDE. Those tend to be for things that are elements. There's only 2 in here that have an IDE, which is hydroxide and alzide. Okay. And also cyanide. Everything else has different endings, okay, which you can either be the 8s or the ites. The other thing you might notice is like acetate, I have 2 versions there. One is your molecular formula way, the other way is your structural formula, so you would encounter both ways written. Let's try naming some compounds that involves polyatomic ions. Let's look at SnSO4. Well, first off, you got to know that SO4 is sulfate, and we have tin. We're going to have to name that as tin. The issue here is that tin has a variable oxidation state, so I'm going to have to tell in my formula what is the oxidation state. Well, SO4 is a 2 minus, therefore tin must be a 2 plus. So then my formula would be tin 2 sulfate, or writing it in the old version, stannous sulfate. Sodium sulfide, well, I got to know what sulfide is, which is SO3 2 minus, and sodium is N plus. So I'm going to need to balance this out, which means I'm going to need 2 sodiums to every 1 sulfide. Na subscript 2 SO3. Ca open parentheses ClO close parentheses 2. Well, I need to know that calcium is always a +2 charge, so I don't need to put any Roman numerals, but I need to figure out what ClO is. That's one of the polyatomic ions. That's your hypochlorite ion. So this would be calcium hypochlorite. Barium hydroxide, and you know what hydroxide is. That is OH with a minus charge. Barium is a barium with a 2 plus charge. So to write this formula, I'm going to need 2 hydroxides to every 1 barium, which gets me Ba, open parentheses OH, subscript 2. Potassium perchlorate. Well, we know potassium is +1. Chloride is ClO4 minus. They're both 1 to 1, so I just need to write that out. Potassium ClO4 minus. ClO4, potassium perchlorate. Chromium, subscript 2, sulfate, subscript 3. I need to figure out what chromium's charge is. It's a variable oxidation state. So if I got 3 sulfates at 2 minus, that's -6. And I got 2 chromiums, that means that chromium must be a +3. So now I'm going to have to put that in my formula, my written formula, when I write it out. So I'll write it as chromium 3, Roman numeral 3, sulfate. Magnesium nitride. Well, this is where you got to think about as you're naming things, and not get in the habit of this following. Since all these have been polyatomics, you're probably thinking this is a polyatomic, but you got to realize this is nitride. As I mentioned earlier, most of the time when it's an IDE, with those 3 exceptions I told you about, it's going to be the elemental. So this is basically nitrogen with a 3 minus. So I got magnesium and nitrogen with 3 minus, which means I'm going to need magnesium has a 2 plus. So that means I'm going to need 3 magnesiums and 2 nitrides. Mg subscript 3 and subscript 2. Not a polyatomic ion, this is a monoatomic anion of nitrogen. Just trying to keep you on your toes to think about it as you name things, because everything's going to be mixed up when you have it on the test, etc. Fe3 subscript 3, PO4 subscript 2. I got to figure out what the charge is on iron. Phosphate is a 3 minus. Okay. I got 2 of those, that's -6, so that means my iron must be a 2 plus. Since this is a transition metal, I'm going to have to put the charge in parentheses in Roman numerals. So this would be an iron 2 phosphate. Or using the older name, ferrous phosphate. Titanium 4 nitrate. That Roman numeral is telling me my charge on my titanium, which is 4 plus. And I know nitrate is NO3 minus. So that means I'm going to need 4 nitrates for every 1 titanium. So my formula would be titanium, open parentheses, NO3, close parentheses, subscript 4. Let's talk about molecular substances and how we name them. Binary compounds composed of 2 nonmetals, or usually molecular, and are named using a prefix system. Named the same as the ionic, except must indicate how many atoms are present, using mono, di, tri, etc. No charges for share. They have share electrons. There's no charges with molecular substances involved in those molecular compounds. But we typically put the more metallic compound first when we're writing the formula. Which way is the correct way to write the following formula based on putting the more metallic compound first? Always when we write molecular substances, we put the more metallic first. It also helps you with naming, because you know you're going to name it in order as well. So if we were looking at NF3 or F3N, going back to that periodic trend we talked about earlier, the metallic more going to the left and down, we know that nitrogen is more metallic than fluorine. So therefore, to write this formula correctly, well, nitrogen would be in front and fluorine would be second. So you would see this written as NF3, not F3N. The name of the compound has the elements in the order given in the formula when you write them out. You name the first element using the exact name, just like we did with the ionic. Name the second element with the IDE, just like we did with the ionic. Except now, if there's more than 1 atom, you must give in any given element, you must add the prefix, di, tri, etc. to tell them how many's there. Remember, there's no charges, so we need to let the reader know when we're looking at the written name, how many of each species is present. Let's try naming some. Okay, here, to name a compound, you must know if it is molecular ionic, so that you know which rules to follow. If you have a metal, non-metal, it is ionic compound, where you name the metal first and then the non-metal, changing the ending to IDE. If you have a non-metal, it is a molecular compound, which you do similarly as ionic compound, except that you must use the prefixes to indicate the number of atoms. One thing to keep in mind as you're naming things, you need to figure out what type of bonding is there. Okay, in this case, you get N2O3. What type of bonding is that? Covalent or ionic? That's covalent. So therefore, we're going to have to use the prefixes. So we got nitrogen. We name the first species just like it is. In the second one, we have to change the ending to IDE, but now we also have to account for the number of species. So this would be dinitrogen trioxide. This is once again molecular compound, non-metal, so we're going to be following these rules and have to put the prefixes. So you name the first one as it is, sulfur, and then you have the second one. We're going to change the IDE, which would be fluoride, but I also need to say how many is there since this is a molecular compound. So sulfur tetrafluoride. Now we have chlorine dioxide, and I'll write the formula. Notice that chlorine is INE because it is the first word, so therefore it's going to be the name of that species. So it's going to be chlorine, and then I have dioxide, so I know what oxide is oxygen, but I need two of those. So we write the formula just as we write it, which would be chlorine, oxygen, subscript 2. Sulfur hexafluoride, you write your sulfur, and then I got hexa, which is 6 fluorides, SF6. Cl2O7, chlorine's first, so it's going to be the word chlorine, not chloride. So it's going to be dichlorine, and I have oxygen. I have 7 of those, so that's hepta. Now, since I'm going to end up with 2 vowels next to each other, we're going to drop the A. So this would be dichlorine heptoxide. Now, HCl gas, it's important I put gas there because I'm following the molecular rules. If I had AQ there, then it'd be an acid, and I have different rules to follow. So we're following the molecular species here. So I have hydrogen, and I have chloride, so this is hydrogen chloride. Okay, let's name this compound, but think about the bonding. Okay, we got magnesium, and I got two Cls. Okay, what kind of bonding is here? Well, we got a metal and a non-metal. So this is ionic bonding. So then we name the first species, which is magnesium, and we name the second one with IDE, which is chloride. But I'm not going to say magnesium dichloride because this is a compound. Okay, so I don't have to worry about that. So this would be magnesium chloride. Ionic compound, no prefixes used. So that's what I say. You have to look at the bonding each time to decide, do I use prefixes or I don't use prefixes? Metal, non-metal, no prefixes. Non-metal, non-metal, use prefixes. Here's some older names you need to be familiar with. Water, H2O, ammonia, NH3, hydrogen sulfide, H2S, nitric oxide, NO, hydrazine, N2H4. In this course, typically if you have hydrogen in front of the formula, we're talking about acids, okay, because we tend to use molecular formulas. But when you get in other courses, you start using structural formulas, that doesn't help. But in this class, it should be fine. If there's a hydrogen in front, then we're talking about an acid. Now you may say, well, wait, water has hydrogen in the front. Does that mean it's an acid? It can be, and we'll talk about that later. Acids are traditionally defined as compounds with a potential H+ as a cation. Binary acids consist of hydrogen ion and any single anion in aqueous solution. For example, HCl aqueous, AQ behind it, is hydrochloric acid. So your naming procedure is hydro, the stem of the species, ic acid. It's that AQ that tells me that this is an acid, and we're going to use these rules. An oxyacid is an acid containing hydrogen, oxygen, and another element. Example, HNO3 is nitric acid. The oxyacids are a derivation of the oxyanions that we discussed earlier. So if you can learn the oxyanions, then you know you can change to the acids by changing the ending to ic and us. If you learn the oxyanions, you can easily adapt to naming the oxyacids. ATEs turn to ICs, and ITEs turn to OUSs. So we know that the oxyanions are per 8 ion, and hypoight. Well, those converts, if you're talking about the acid, to a per ic acid, or ic acid, an us acid, or a hyper-us acid. Examples: the nitrate ion, NO3-, if I add a hydrogen to that, now it becomes an acid, and we would take that 8 and change it to ic, so it's nitric acid. NO2-, nitrite ion, if I add a hydrogen to that, I get HNO2, it's nitrous acid. ClO4- perchlorate ion, if I add a hydrogen, I get HClO4, that's the perchloric acid. For some species, there is a change in spelling in the name. SO42- sulfate ion, I add the hydrogens, I end up getting sulfuric acid. PO43- phosphate, phosphoric acid. Hydrates. A hydrate is a compound containing water molecules weakly bound in crystals. Hydrates are named for the anhydrous compound, followed by the word hydrate with a prefix to indicate the number of water molecules per formula unit of the compound. Example: CuSO4 5H2O. Okay, this is a hydrate because it has that little dot in the water molecules. We named the CuSO4 just like we did previously. Okay, so that would be copper 2 sulfate or cupric sulfate. Okay, and then I have to put my hydrate behind it, and how many. In this case, it would be penta. So you got copper 2 sulfate, pentahydrate. If I go the other way, I would write the formula the same way with my species. So the magnesium sulfate, magnesium is a 2+, sulfate SO4 2-. So that formula would be MgSO4. And then I have my little dot, and then in this case, heptahydrate will tell me I got 7 waters. MgSO4, 7H2O. Homework 15 to 18.